Number 1, this one is very similar to the your turn problem that we did, where we're traveling in a bus and we tend to lean forward if the bus suddenly stops or slows down. So same idea here. If you have a train and you have a piece of luggage that's in the train, well, initially they're both moving, let's say to the right. So then if the train suddenly slows down, then that means it has an acceleration this way. And if there's not much friction between the luggage and the floor here, then there's not really any force acting on the luggage, and it's going to keep going straight. So it's going to look as though it is moving towards the front of the train. Number 2. So this one has to do with Newton's third law that says that if you have two objects, so objects 1 and 2, let's say the car and the truck, then they're each going to exert a force on each other. So call this, for example, F21, the force from object 2 acting on object 1, and F12 over here. And Newton's third law says that the two forces will have the same magnitude, but will be opposite in direction. Number 3, here we have keywords that we're looking at is constant velocity. So if you draw a free body diagram for this one, now it doesn't say if the hill is smooth or if it has friction, but it doesn't really matter. If we're trying to push the car up the hill, we're going to apply an applied force this way. There's going to be a normal force perpendicular to the surface. There's going to be a weight straight down. And for now, let's assume there's no friction. So if we're at constant velocity, that means we're in equilibrium. That means the sum of the forces is 0, in this case in both the x and the y direction. So if we just look at the x direction, we have the weight here has an x component, wx. Sometimes I call it fgx. That's that x component right here. So if there's no friction, that means that this x component of the weight must balance out the applied force. And the net force must be 0. If there is friction, then it just means that it would be kinetic friction because the object is moving, and that means that the applied force would then be equal to the weight in the x direction plus the friction force. But in any case, the sum of the forces must be 0 because you're moving at a constant velocity. Number 4, we have another key word here is that you have an unchanging velocity or a constant velocity. So if you're in an elevator, and that's you in the elevator, here you've got the force from the floor, which we usually call the normal force, and then we have the weight. Well, if we have a constant velocity, we're in equilibrium, the sum of the forces must be 0, and these two forces must balance out each other. So D is the best answer because it shows that the forces are the same length. If you look at letter C, for example, it shows a stronger normal force than weight. So if you look at this one, it means that the net force here is in the upward direction. So that means that this scenario is actually the elevator is accelerating upward. And this one is actually the elevator is accelerating downward. Let's do one more. Two identical masses are attached by a light string that passes over a small pulley. Alright, so the key word is we have a frictionless surface here. And what's the acceleration of the masses? Well, we know they have the same acceleration because they're connected. So let's just consider the hanging mass and draw a free body diagram. It's going to have the weight going down, and it's going to have a tension going up. I'm not drawing the arrows to scale this time. but we know that it's going to be accelerating downward because the force of gravity is pulling this one down. And since there's no friction, there's nothing slowing it down. If there had been some friction here, right, if there had been some friction, then it's possible that this friction could have balanced out this weight and that it could be moving at a constant speed. But if there's no friction, then there's nothing to balance out that weight pulling down here, and it's going to accelerate. Now, if it were in free fall, then the acceleration will be g. But since there's a mass attached to it, then this mass is definitely going to slow down the hanging one. So there's no way that it's going to be accelerating faster than g. So the answer has to be B. Now, if you like to see equations, then you would just write Newton's second law based on your free body diagram here. The sum of the forces equals ma, and we're going to have the weight that is causing this acceleration here and the tension that is opposing the acceleration. I'm going to make it negative, and that's the sum of all the forces. That's equal to ma. So if you solve for acceleration, then you're going to get mg minus t divided by m, right, if you solve for a. So what you're going to get is you're going to get g minus t over m is what your acceleration is, which is definitely smaller than g.